All right, thank you so much. It's welcome back from lunch, everyone. I know it's just after lunch, and they've turned the heaters on up here, so I'll speak in a nice, soft, even tone so everybody can get a good nap in after lunch, and then you'll be revitalized for the next session after mine. I'm going to talk about one of the most difficult problems that we see in architectures like microservices, but it also has sort of deep resonance with the theme of this conference. How do you get to the right level of granularity for your services in microservices? And then once you figure that out, how do you get them to successfully talk to one another? I'm going to talk about both those things briefly today. I go into a lot more depth in this, obviously, in our book, Software Architecture, the Hard Parts, but this is a brief summary of the material in that book. This is one of the trickiest problems we find with teams because what size should my microservice be? Well, the common answer is that, well, it should be single purpose. Okay, but are all messages single purpose, or all customer messages single purpose, or is each kind of customer message single purpose? Because you could have a philosophical argument about any of those being single purpose. That's not great advice. But this gets to the kind of heart of what this conference is really about, because a lot of people, certainly in the early days of Agile, thought that Agile meant no architecture at all. You don't need architecture. And it turns out that's not true. If you're trying to build a 50-story office building, you need architecture versus a doghouse where you don't need architecture. But what agility in architecture really means is not the lack of architecture, it's the ability to do iterative design in architecture. I don't know any architects that are so clever that they can look at a difficult problem and the perfect design just falls out of their head into a drawing tool somewhere. What you need to do is create a candidate design and then iterate on that design. And what you need to iterate on that design are tools. So I tell architects what you need to think about is I have a toolbox that I have at work that have some generic tools in it, but I'm gradually filling it up with very specific tools for the place that I'm in. We call these tools integrators and disintegrators for granularity. Disintegrators are forces that encourage you to break them down into smaller and smaller pieces, and integrators are forces that encourage you to bundle them back up because you've broken them down too far. I'll give you 5 disintegrators and 3 integrators, but I want to stress that this is never going to be a comprehensive list. These are pretty generic. You should start looking for the specific ones in your organization because they're there. The problem in architecture is there's no such thing as a generic architecture. Every software architecture is hyper-specific, and a lot of the integrators and disintegrators you end up developing will be hyper-specific to that architecture. But at the end of the day, getting good at generic architecture doesn't do your organization very much good. Getting really good at the architecture you're working in is a tremendous benefit. So let's look at disintegrators. And the first one of these is the obvious one, which is service functionality. This is what happens if you go crazy with the refactor extract method settings in your IDE and start breaking things down into smaller and smaller pieces. So the idea here is maybe we have a notification service that has text, email, and postal letter, and we decide by service functionality, okay, let's break that into 3 separate services. That seems like an appropriate level of granularity. It should be noted, though, that these tools should not override reality or some other stronger force. So we almost think about this as strong and weak nuclear force in physics. Because, for example, if you have a customer service, you might be tempted to break that down into profile, comments, and preferences, but now you've lost the idea of customer. So it should be customer profile, customer, because you don't want all profile there because now you've broken it and created a different kind of granularity. So domain concepts still apply strongly here. So service functionality is the easiest one and most obvious one, and this is the one that gets a lot of teams in trouble because they go too far. And then they end up with a microservice architecture that's too fine-grained. And because of data fidelity, now they're pushing a lot of data around on network and REST calls and event queues to no good purpose. So let's look at another disintegrator, code volatility. This one's interesting because it doesn't have much to do with the structure of the code itself, but rather how volatile that code is. So for example, if you look at something like notification service and it turns out that code rarely changes in text and email, but because of bizarre legal problems, it changes all the time in the postal code. And so I might consider breaking that down by volatility into one versus the other, where code rarely changes and code changes all the time. Now, two slight digressions about this. One, you keep hearing these little mini cults grow up in software architecture. And one of those little mini cults is volatility-based decomposition. There are a lot of people who say that's the only thing you should look at is volatility-based decomposition, but it's just another one of our disintegrators. It's applicable sometimes, but not universally. You have to be careful about these things that are universally applicable in our world. So don't join the cult, but it is a useful tool. The other thing that's an interesting side observation about this is that we talk all the time about evaluating trade-offs in software architecture, and this is a classic blind spot because reusable code is great, right? That's a force for good in your organization, right? Because the more code you can reuse, the less you have to rewrite. Everybody gets the abstraction part of reuse right, but misses the most second part. It has to have low volatility. Because if you reuse something that's constantly changing, everything that reuses has to stop and coordinate around that change. So that's another indicator of volatility, is good candidate for holistic reuse because it doesn't change very fast and it doesn't cause these rippling side effects in my architecture. So volatility is the second disintegrator. The third one we called scalability and throughput, but this is really this whole family of what we call operational architecture characteristics. So that's what Mark and I call, what some people call non-functional requirements or system quality attributes. It's really the capabilities of the architecture versus the behavior. And the reason those are important is because, wow, this room has sound effects. That's cool. The reason that's important is because there are some problems that can be solved with design or architecture. Security is a great example of one of those, because if you have a monolithic application, you can build one part that has better encryption and hashing and salting and all those kind of best practices and governance. Or in a distributed architecture like microservices, you could build a service that has stronger authentication authorization, is more hardened. So security can be solved either with design or architecture. But high scalability can only be solved with architecture. Elasticity, to a certain degree, has to be architecture, because a monolith just cannot grow to that level. That's what these things are. These are the things that you really need to distribute and break apart to be able to support those kind of things. For example, let's say we have our notification service. We have 220,000 texts a minute, 500 emails a minute, and one postal letter a minute. So you could break those down into individual services. Now, I'm going to go back one there. You may think that, well, you know, I could put email and letter into one service because they have more or less the same magnitude. But again, remember the strong, weak nuclear force thing. What would I call it? Non-SMS communication? That's a terrible name. You should never name something because of what it's not. And so, again, the sanity of design would probably trump this and say, yeah, it should be 3. If it can't be 1, it should be 3, and not some random collection of 2 of them. A third of these is a specialized case of those, which is around fault tolerance, availability, and reliability, and that family of characteristics. So for example, if I have a notification service and for various reasons the email part of this is very prone to throw a stack trace, and of course when that happens inside a single process, everything is all done. And of course, if you split those apart, you can control that a lot more, because if email goes down in its own service, the others are not affected. And in fact, you can even do architectural tricks like use message queues and durable message queues, and when it comes back up, deliver the messages to them. But it is a way to think about availability and reliability as a good way to break those things apart from an operational standpoint. And then finally, security, which is a common concern in a lot of ecosystems like this. If you have a profile service with info and credit card info, you may want to break those apart and make the credit card part of that a lot more secure, because obviously it has to do with something that nefarious people might be interested in. So those are 5 sample disintegrators. Like I say, this is just the starter set for your toolbox, you should start actively looking for these, because these are the things that allow you to create a candidate design and then say, should I apply one of these tools to it to see if I can break it down further, or do I need to bundle it back into an integrator? So let's talk about 3 integrators. The disintegrators are more obvious to developers and architects, it seems, than the integrators. The first of these is the most obvious one in the microservices world, which is transactionality. The thing that really distinguishes microservices from other distributed architectures, because we've been using events for messages forever, the thing that distinguishes microservices is the data fidelity. This bounded context idea that says the data has to be inside the service boundary, which means that transactionality is now an architectural headache. It's not something we can just push off to a database somewhere. And in fact, the entire second 2/3 of my talk today is about exactly that headache. But very often you discover this in microservices. In fact, this is some of the most common advice you get in microservices. If you have 2 services that need to share information, but when I register a new customer, I have this password service, you shouldn't be trying to do these kinds of transactions across service boundaries. Now you can, and I'll show you how, but in general, you want to try to avoid this. So as soon as you encounter this, the first question you should ask is, oh, well, could I bundle that back into a single service and get rid of the distributed transaction? But now I may need to apply another disintegrator to this because it's too big or it's too volatile, or so. Now you can kind of see how this iterative design process works. You have tools that kind of are opposing forces to each other. The other really common one in microservices is data dependency. This is, of course, because of this data fidelity problem in microservices. So let's say you have one service like this, but we know that mostly it's not just that, it's also mapped to some relational database somewhere. So I decide I want to break this thing apart. That's nice and easy in an IDE, carve it apart with your refactoring tools, etc. But now I've got to handle all of this. Well, what I need to do is look at who writes and who reads. So let's say that function A writes to 1, 2, 4, and 6 and reads from 5. Function B writes to 3 and reads from 2 and 5. And C writes to 5 and reads from 1, 2, and 3, it looks like. Well, let's just move these over in terms of ownership. So A owns 1, 2, 4, and 6. B owns 3, and C owns 5. But now I have all these read relationships left. What am I going to do with those things? Well, I could just let A directly access the database over there in C, but you can see exactly where that's going, into a big ball of mud. And so maybe you just want to bundle these back together. Maybe the data dependencies are too hard to pull apart. This is what happens to a lot of service teams when they try to break things down. The code works great, but you can't get the data broken down to that degree. Or you can't convince some data developer somewhere that that's a good idea, which is a hard argument in some organizations. Just a side note, one of the big arguments you have about that is about things like referential integrity and foreign key constraints. But here's the way to get around that argument, but good luck. It's really just a form of governance. Referential integrity, and you're just really used to the database doing that. But we can do that in code too and make it just as reliable with fitness functions. That's not the only way to solve that problem, although every database developer thinks that is the only way to solve that problem, but it's not. And there's a whole bunch of our book. This is actually more complicated than any of the code stuff, so there's a whole section in our book about one of the things you have to start focusing a lot in microservices is who writes to data, who has access to it via reading it through caching or through some other mechanism that doesn't get them tangled up in dependencies or transactionality. And then the third of these is workflow and choreography. And this is something we were late to the game with, and you'll see more about this in the second part, that, okay, I have this one service that's doing a bunch of work, and I decide, it's too big. I want to apply the service functionality disintegrator to this thing and break it up into a bunch of smaller pieces. This is exactly what a lot of very early microservices teams did. They went crazy with this idea. The problem, though, is that to get useful work done, these things still have to talk to one another and do data processing, but that all happens at the network level now rather rather than in process, and that's a lot slower. So for example, if the regular processing over here takes something like 1500 milliseconds, it's not at all unusual for something over here to take a lot longer because I'm doing all these network hops and consolidating information and returning it, and so sometimes multiple times performance. This is the entire thing you hear all the time about performance being one of the headaches in microservices. Scalability is great, but performance or responsiveness is sometimes a problem like this. The other problem you have is data consistency. I'll talk more about this in the second part as well. But if I'm trying to write something and one of these is down, what happens? Well, there's lots of different patterns and ways you can solve this problem, but you got to solve it. Whereas in the single service, it's either up or it's not, and so you don't have to worry about these problems from the fallacies of distributed computing. It turns out that the more complex your workflow is, the more you benefit from something like orchestration, but we'll get to that in just a second. So this is a great example of what we mean when we talk about iterative design and software architecture. You need tools, you need a toolbox, and you need the ability to iterate, because what we've really learned from agility over time is that, so when you're building software, you're building something that has hundreds of thousands or millions of tiny moving parts, and it's never actually been built exactly before the way you're building it, because if it had, why are you building it again? So you're in this exploratory phase always. So when you're exploring, you need the ability to do incremental change and get fast feedback. And that's exactly what this lets you do. The design phase, before we started writing code, is to look at the design and iterate on it to see if you can reach a better place. So that's all about what we call static coupling. This is the granularity part of microservices. And that's the first half of our hard parts book, is how do you resolve the static coupling in an architecture like this. But now I want to move to dynamic coupling. When you've got the granularity of these things established, how do you effectively get them to call one another? And this is something we spent a lot of time on because it exhibited some unusual characteristics. So let me talk about each of these three, what we ended up calling primal forces in dynamic coupling in architectures like this. They are communication, consistency, and coordination. And I'll talk about them in turn. I'm going to do a brief overview of these because what I want to get to are transactional sagas and how to make decisions about that. But before you can get there, you have to resolve these three things for reasons I'll show you in just a second. So let's talk about synchronous versus asynchronous communication. So here's what we're really talking about when we talk about this from an architecture standpoint. So let's say that I have a blog and I'm allowing people to post comments on my blog. And so in the synchronous world, I type in my comment, I post the comment, 50 milliseconds to get to my comment service, 3,000 milliseconds to update my comment, and 50 milliseconds to get back. So 3,100 milliseconds round trip for that synchronous, maybe restful call to update my blog. Let's do it asynchronously with a message queue. I'll type in my comment, hit the enter key, 25 milliseconds to the message queue, 25 milliseconds back, and we're done, and back to work again. Notice that this is a common magic trick that architects pull, because now the user thinks that I'm a magician architect because the performance of this thing is stunning now. And I haven't actually improved the performance at all, because it's still going to take another 25 milliseconds to get to the thing and 3,000 milliseconds to update it, but I've improved responsiveness. And that looks magical. And that's easy, whereas improving performance is hard. Because first, I got to figure out why the performance sucks, and then I got to figure out how to make it better. And those are two hard problems. This is way better and much easier, but like a lot of superpowers, it comes with kryptonite. And the kryptonite, of course, is I've lost that request response cycle, because what happens if somebody types a bad word into my blog? In the synchronous case, I can catch that and send them an error message back because I'm holding on to that. In the asynchronous case, they've already gone on and started doing other stuff. Now, I could create another message queue and have my application listen to it for potential error messages, but now my application has to be multi-threaded and has to interrupt whatever, and so it's too hard. I'll just send them an email tomorrow and tell them they said something bad, or it's a lot more complicated. So that's the trade-off you often get between synchronous versus asynchronous processing like that, is that kind of trade-off. So that's synchronous versus asynchronous. Now let's talk about distributed transactions and consistency. Now, for a lot of reasons, you can't do ACID in distributed architectures like microservices because of cap theorem and a whole bunch of other interesting stuff. But you can fake atomicity in distributed architectures by implementing it yourself. And this is what it looks like. So let's say that I have this workflow and I'm trying to achieve the transactional scope that is around that red dotted line right there. So in the happy path, I make a call, and let's say these are all synchronous calls. I make a call that's blocking. I update one service, I update the other service, I update a third one, and then I return, this was a successful workflow, and here's my result. In the unhappy path, though, I update my service, I update one, I update the second. When I try to update the third one, I get an error of some kind for whatever reason, but I don't even care what the reason was. Because I'm trying to achieve atomicity at the entire workflow level, I'm going to now have the orchestrator go back and undo the stuff that I did before and do compensating updates. This is what's referred to as a compensating update framework, and undo so that by the time this workflow is finished, it looks like nothing ever touched anything. That's atomicity in distributed architectures like this. And only then can I return and say, hey, we were in an error state. Sorry, we couldn't do what you wanted to do. But what does eventual consistency look like in this world? Well, in eventual consistency, the transactional boundary is just around the domain service. And you can still have them collaborate in workflows, but there's a big difference here in terms of responsiveness. Now, we're still in synchronous land here, but this is much better responsiveness, because what happens when I get an error here, I can immediately return to say, hey, I'm in an error state, and then let the orchestrator go back and clean up those services with compensating updates, because I'm not trying to achieve atomicity at the entire workflow level. It's okay if some of these are not consistent for a short amount of time, because it's eventual consistency. That's the idea behind eventual consistency. And we'll see that this has a much less damaging impact on your architecture. Not surprising, there are tons of patterns for eventual consistency. This is one of the most common pattern categories you see out in the world. Because here's the problem with eventual consistency, of course, one of many problems. Let's say that I have this distributed architecture like this, and I delete customer 1, 2, 3, but what happens to the customer 1, 2, 3 over here? I got to figure out a way to get rid of those, of course. Now, some people use some sort of background synchronization process, often sponsored by your database vendor who has a tool that does all this background sync stuff for you, so that it automatically picks this stuff up for you and will get rid of it for you if you need to. The problem with that, of course, is if you're using some sort of mechanism like that, you're highly coupling the database schemas together, which is coupling in a way that's not desirable in the microservices world, and so buyer beware there. So maybe you're better off setting up your own event-based synchronization where you have a durable message queue that whenever you delete one here, it goes and cleans up and deletes the rest of those for you as it needs to. So as I said, there are lots and lots of patterns for this that exist in the distributed architecture world at microservices. So the third of my primal forces are distributed workflows. And this one was a little surprising that this ended up in there, but you'll see why in just a second. So this is the answer to the fundamental question, should I use orchestrational choreography my workflow? Now, in microservices, you never use a global orchestrator like an ESB. You use an orchestrator service per workflow. And of course, it's named metaphorically because an orchestra has a conductor. Each instrument has a very simple job, and they do it and they coordinate around the orchestrator, whereas choreography is like dancers. They have a plan and they know how to carry that out, but there's no central coordination necessarily. So let's talk about each of these. And for all of these kind of design, the happy path, the and the error conditions are the interesting things to look at. So let's look at a simple order fulfillment workflow, and we'll look at an orchestrator, and this orchestrator owns the state of the workflow. So this is just a regular microservice, but it doesn't have any domain behavior except owning the state of the workflow that it is orchestrating. So, and generally one orchestrator per major workflow. So my co-author Mark comes in to place an order for a book. It makes a call to an order placement service and then updates its state to an order has been created and then tells the customer it's been created. Then it makes some calls synchronously or asynchronously. We'll dig into that in just a second. To, for example, a payment service and get order paid. And then go to, that changes the state here to payment applied. Then we'll go to a fulfillment service, which will then ship the order, move our state to order shipped, and then finally email them, congratulations, you've ordered a book and it's on its way to you, and there is our completed order. But what happens if we're in a back order state? We don't have inventory. So we're at the payment applied state in my workflow, but when I try to go fulfillment, there's no more items. Now the orchestrator needs to go back, first of all, and email the customer and say, sorry, it's back ordered, but now needs to go back to the payment service and say, would you refund them, please, because we've applied payment, we don't actually have the thing to ship to them. So would you clean that up for me? Notice that the orchestrator is really handy for this kind of stuff because it knows what state the workflow's in, it knows all the collaborators that are working here, and more importantly, it needs to update the order as well. More importantly, I didn't have to add any additional communication to this to handle the errors and the boundary conditions. All the paths were already there. I just used the roads that were already in place. That's important because now let's look at choreography. The choreography has no orchestrator. This is just each service managing its own state, and then you probably emitting events that other services pick up in this kind of organic workflow. So place an order to an order placement service. It then updates its state in order placement and then sends a message over to payment service. Hey, I just placed an order. Who's interested in that? Payment says, I'm interested in that, and it'll pick it up and apply payment. And then chain over to fulfillment service, which will ship the book, and then to email, tell them, congratulations, here's your book. Initially, this looks fantastic, doesn't it? Wow, it's so clean and simple. It's exactly like the way I think about the workflow in my head, so this is really, really nice. Until you get to the error and boundary conditions. What about back order? So payment is applied, I've paid the order, but now I get here and back order. Now the fulfillment service has to know about sending an error message to email, but it also now has to know that I need to send a message back to payment to tell it to update the payment status. So each of these domain services in choreography have to be a lot more aware of the workflow they are within for exactly these reasons. They can be much dumber in an orchestrated world because the orchestrator handles those details for them. But it gets actually worse than that because where is the state of my workflow? I call up and say, hey, I ordered a book, but it hasn't shown up. Where is the thing? Well, you probably want a state owner somewhere, and it is definitely the order placement service. This is so common, this pattern is called the front controller or front orchestrator pattern, but now it's even worse because now you have to update that thing every time something happens. Notice what has happened here is that all these additional communication points grew around it, and it's exactly the same ones we had with the orchestrator, pretty much. So just changing from orchestration to choreography does not automatically make it less complex. The complexity is still there, it's just spread out and distributed in different places. So responsiveness, scalability and throughput, and better fault tolerance in choreography, because there are fewer potentials for bottlenecks, a better workflow and state management, easier error handling, and better recoverability over here for orchestration. Okay, so now let's culminate all these things together. So Mark and I, we were writing this book, wanted to say something interesting about this idea of sagas. Chris Richardson, in his Microservice Patterns book, used that term sagas, which was borrowed from the database, the distributed data world, but it's stuck. It means a transactional workflow in microservices. And Chris Richardson identified two kinds of sagas, orchestrated and choreographed. And Mark and I were doing a bunch of experimentations with versions of these things, and we kept noticing an interesting phenomenon. It's sort of like studying fractals and the sensitivity to initial conditions thing that fractals have. The butterfly flaps its wings in China and we get a hurricane here. Because it seems like in these workflows, when you model them, you change one little thing and all the trade-offs shuffle in a way that seems disproportionate to the kind of change that you made. And we realized the reason for that is that we've been trying to change these independently of one another, and you can't. Because these form a three-dimensional conjoined space where all of them affect the others because they're all coupled to one another. And when you're making a decision in distributed architectures, you're placing a ball in this space, but you can't just move it anywhere arbitrarily because there's sort of gravity around the axes. And what made us think we might be onto something interesting here is if you look at a non-distributed transactional workflow, it's orchestrated, synchronous, and atomic, and it would form exactly 0, 0, 0 in my space here. And so it's only when you move into the distributed world you have to start thinking about this. So when you think about, let me go back one here, we have 3 different states that have 2 extremes on the spectrum. That means that if you know anything about combinations, we have 8 different possibilities. And so Mark and I thought, let's just model all 8 of them. Figuring that more than half of them would just fall away as improbable or impossible combinations. And it turns out that wasn't true. They're all legitimate patterns or anti-patterns in distributed architecture. So we gave each of them sort of a whimsical name for what kind of saga it is. These are all different kinds of stories, and each of them has a different set of trade-offs. And I'll do this in the amount of time I have left. We'll talk about each of these, and it's always these 3 forces and changing one at a time. So the epic saga starts with synchronous, atomic, and orchestrated. And so when you make a happy path call here, notice the dotted line is the transactional scope. These are all blocking calls, and so we're waiting and waiting. So think about this workflow. If each service takes 1x to execute, how long does it take this workflow to execute? 3x. Because everything's blocking and waiting, blocking and waiting. And this is exactly like the example I showed you of atomicity before. We're going to make a call and block and wait, and make a call and block and wait, but now we have an error state. Now we need to do compensating updates. But notice I can't really tell my caller that I'm done yet, because one of the additional fallacies of distributed computing is that compensating transactions always work, because they don't. So you have to worry about, okay, there are 2 potential error messages here. One, I couldn't do your workflow for some reason, or even worse, the compensating update didn't work, and this is the appropriate time for the HTTP status code that says I'm a teapot, because that means I don't know what state we're in now. It's teapot time. Notice that because of that atomic scope, that if I'm in this state of the workflow where an error has occurred, but I have not had a chance to fix it up yet, if someone else queries that domain service, they're going to get delta -1 back. Now, whether that service holds on to it or the orchestrator does, but they're not going to see any effects of this workflow until it's completely done. That's what we mean by atomic. So this is a long-running heroic story. It mimics non-distributed transactional interactions. This holistic transactional coordination increases coupling a lot. It's really easy to understand, but really difficult to implement correctly. So for each of these, we give a use for what these might be used for. And this chart down here of sort of characteristics, these are the 4 architecture characteristics that seem to change the most as we went from one to the other. And so this is often the first attempt by teams because, hey, this looks like regular non-distributed calls, but it's very slow. It is useful in environments where every step has to be completed before you move to the next step. So kind of wizard interface where the output of this one is the input to the next one, and you have to finish it before you go to the next one. Or where absolute transactionality is more important than responsiveness, because responsiveness is bad in this, is in fact the worst you can get just about in this architecture. So let's move one of the sliders. Let's move some synchronous to asynchronous communication. Still have atomic scope, but now we're asynchronous, and now we can do multicast, because now things can happen asynchronously, which means now if each of these services take 1x to execute, this whole workflow is 1x. or it's as fast as the slowest service, which is significantly more responsive. In the error case here, whoops, I went one too far there, did I? In the error case, again, I can take advantage of these multicast capabilities and clean the stuff up much more quickly than I could before because I'm not doing all that blocking, etc. But I still have to wait because of the atomic scope before I send that message back to my consumer saying everything is finished. This is a complex story that's hard to believe in the end because when you go asynchronous, you can't, sometimes things get out of order and it's just a little bit confusing. A lot of times this will improve performance but introduce concurrency. So teams say, hey, I've heard that the way you improve performance in microservices is go to asynchronous, and it's true, it improves responsiveness. But now you have deadlocks and race conditions and a whole bunch of other beasts from the concurrency world, which may actually be worse than your performance problems were. This one's really useful. A lot of times this is the first attempt at trying to fix an epic saga. Noticeably better responsiveness because we've gone concurrent, but not a good fit if order of operations is important because everything's going to be happening all together now because of asynchronicity. Why isn't responsiveness better here? Well, it is 1 star better than what we saw with the epic saga, but it turns out that the thing that's really killing the responsiveness is the atomicity, and we'll see how to do some analysis around that just in a bit. Next, we're going to move communication back to synchronous, but go to eventual consistency. So now the transactionality is at the service level, not at the workflow level. And so, but I'm back to synchronous communication, so all these slow blocking calls. You know, when these are animated like this, even the animation of this workflow is slow and non-responsive, which is a good indicator of the way it works in the real world as well. In the unhappy path here, notice, whoops, I went too far there again, didn't I? Sorry, I'm trigger happy today. In the unhappy path here, notice that even though I'm doing all these synchronous calls, as soon as I realize I'm in an error state, I can go ahead and send a message back saying, hey, we couldn't do what you're wanting to do. I'll fix this up for you while you're doing other stuff. Now, there is a possibility here that the compensating update wouldn't work, so you need some error path to handle that if you want to, but this does give you an opportunity for better responsiveness, even though you're using all this synchronous communication. Notice that in this workflow, when we get to the point where I'm in an error state, but I haven't cleaned up the services yet, if somebody queries this service, they're going to get delta back. So we're eventually consistent. It's okay for them to be out of sync at a workflow level for a short amount of time. Fairy tale's an easy story with a pleasant ending. Synchronous plus orchestrator are the easiest ones to reason about. And so the uses for this are pretty broad. This is well suited for most medium to complex workflow. The orchestrator can become a bottleneck, which is why it doesn't work as good at scale. This is the one, the orchestrated pattern in Chris Richardson's book, and the default for many situations, and it makes sense if he's only showing one of them, and you can see why it's the default. It has some really good marks on some really desirable things. This is why this is a pretty attractive option. So as you notice, we put all the orchestrated ones together, so this is the last of the orchestrated ones, and here we'll go to asynchronous and eventual consistency, and this looks a lot like the one before, except that instead of synchronous, we can go asynchronous and do much faster multicast for both error conditions and for happy path. That's the advantage of responsiveness in asynchronous behavior like that. So multiple stories running at the same time. The orchestrator allows for complex workflows with concurrency added. This one is highly attractive for complex workflows at high scale. Difficult if ordering of updates is important, and 2 of the 3 coupling drivers are minimized there. The complexity here is due to a concurrency. One of these, so this is the phone tag. This is our first choreographed one. And notice here, we got back to sync and back to atomic, but we lack an orchestrator now. So I'm sorry, I short-circuited that one, but nothing interesting happens there. The next one's the interesting one. I'm running short of time, so. Here, because I'm doing synchronous calls, I basically have to chain back the way I came, which is not terrifically efficient. This is like a game of phone tag. And middling performance and middling characteristics. It's really not at all common because it's kind of weird to have choreography and synchronous together. And you can see why it's not common, not terrific scores on anything. There has to be one that's objectively the worst, right? And that's the horror story. So why is this one so bad? It's asynchronous communication, atomic transactionality, and choreography, atomic and asynchronous. The reason it's so bad is the error cases, because everything is asynchronous and everything can happen all the time. So, for example, why is this thing so bad? So let's say that I'm in the middle of a workflow. Well, this is just the error path workflow. So, there are a bunch of different options for this. So let's go to what makes this so bad. So I'm in the middle of a workflow here, and let's say that I'm working on this green workflow. So there's a green request that's come in, but everything's asynchronous. So a brown request can come in and a blue one. And now I've got to juggle all these because I don't know if these have resolved yet. And now another green one comes in that's contingent on the output of the first one. And that's when your head officially explodes. So this is trying to achieve atomic workflows without a coordinator. This is all the bad stuff kind of layered on top of one another. Middling performance coupled with impossible to reproduce errors. So this is really bad news. It's very much an anti-pattern. Pretty much a well-intentioned but flawed attempt to achieve high performance with atomicity. So in the interest of time, I'm not going to show you the last two of these because they're not as interesting as this one, because I want to get to here. This is the real benefit of doing this kind of analysis, because you can understand the entire space and look, for example, to say, well, you get this advice all the time that, well, maybe responsiveness is the most important thing that you're interested in. So you look at something like the parallel saga or the anthology saga, but so parallel saga seems best because, oh, I also want orchestration. So this gives you a way to kind of slice and dice this problem space. I can now choose between orchestration and choreography to get some of the characteristics that I want. But the other interesting thing about doing this kind of analysis is that it gives you a feel for what really drives complexity in these kind of architectures. Because if you look at the good versus bad magnitude of consistency, coordination, and communication, by far consistency is the biggest headache. The other two are rounding errors. Getting that right is the toughest thing in a distributed architecture like this, which is why eventual consistency is so favored. This is an example of what we refer to as qualitative versus quantitative analysis. In the perfect world, you'd measure real things that you've built, but what if you haven't built it yet? Using qualitative analysis, it allows you to look at, well, I don't know exactly how much more scalable this one is than this other one, but I know it is more scalable, and that gives you a basis for making some decisions and gives you this opportunity, once again, to do iterative structural design in software architecture. So I'm out of time, so I will now open the floor to questions. Thank you very much for having me. Thanks.
Thank you very much, Neal. So there is one question. So do you have any thoughts on mixing sync and async calls?
Yes, the ones I've showed you here, because I only had 40 minutes, are the pure either one or the other, but we do talk about hybrids as well, because mostly in the real world, you are going to do hybrids, but it gives you a chance to look at trade-offs and, you know, the pockets of trade-offs that you can look at. So yeah, it's most common. In fact, something like the Epic Saga, it'd be crazy to do synchronous compensating updates, because that would be the slowest thing ever. So you'd go asynchronous there for sure. So yeah, very commonly.
Okay, that is it. You did such a thorough job. There are no many questions left.
I've stunned everyone into silence. All right, thanks for having me.
Thank you so much, Neal.
Thanks.